Good day, dear students. We are continue our lessons. Today is lesson 16. The theme 15, but lecture number 16. We continue theme 15. We start item control of thread parameters. So the accuracy of cylindrical threads is controlled using differential and complex methods. With a differential control method, each thread parameter is checked separately. Average diameter, pitch, and half profile angle. To determine the nominal pitch size of the thread and with low accuracy its profile, use thread templates supplied with sets with threaded pitch from 0.4 to 6 millimeters. It's like in figure 15.18, it's controlled threaded pitch using templates. The average diameter of an external thread can be measured using threaded micrometers with inserts the 3 or 2 dart method, as well as on universal and instrumental microscopes. A thread micrometer is used to measure the average diameter of a triangular external thread using the direct absolute method. Measuring range from 0 to 350 millimeters at 25 millimeters intervals. The thread micrometer kit includes special inserts. Inserts are selected according to the pitch of the controlled thread. The prismatic insert is installed in the heel hole. The conical insert is installed in the micrometer screw. Before measuring the average diameter of an external thread, the thread micrometer is set to 0. For accurate measurements of the average diameter of an external thread, the 3-wire method is used. In 3 wires located in the recesses of the thread, measure the distance between their 3 points protruding forward. The average diameter is then determined mathematically. The set consists of 3 wires of the same diameter, like in figure 15.12. Wire diameter is wires. So wire diameter D suffix AP. Wire diameter. It's measuring threads using 3-wire method. Wire diameter selected depending on the thread pitch. P, not R, P. Thread pitch. The thread pitch and half of the profile angle are controlled as a rule using microscopes or projectors. To control internal threats, in addition to the above mentioned devices, an indicator threat gauge is also used. The main method of monitoring the parameters of external and internal threats in production conditions is control using a set of gauges. With the integrated method, the average diameter pitch, half of the profile angle, internal and external diameters are simultaneously controlled. Control is carried out using boundary gauges. Thread gauges have a pass-through PR and non-pass-through, go and not go side. Continuous threaded plugs have a full thread profile and longer length. Blank or workpiece thread plugs have a shorter profile and length, which eliminates the influence of profile angle and pitch errors when controlling the average thread diameter. The non-passable ring is also shorter and has a groove in the middle. Rings can be unregulated, solid, or adjustable. The go-through side, PR, of threaded gauges must be freely screwed into a controlled surface of a controlled size, and the non-go through side, no-go, must not be screwed into it. Screwing one or two threads from the end of the part is allowed. For external threads, the kit includes a limiting smooth clamp gauge or ring gauge that controls the outer diameter of the thread, like in figure 15.21a, and complex thread ring gauges that control the tolerance of the average diameter, like in figure 15.21b. So, inspection of external thread gauges, A, outer diameter, B, medium diameter. A set of gauges for monitoring internal threads includes smooth boundary plug gauges for controlling the dimensions of the internal diameter in figure 15.22a, and complex thread plug gauges for controlling the tolerance of the average diameter, like in figure 15.22b. The dimensions of K connections are checked in individual production, universal measuring instrument, and in mass and large-scale production, special gauges, like in figure 15.23, 15.24. On the figure 15.23, you can see control of K-way on the shaft using gauges. Control is carried out element by element with limit gauges as well as with complex K gauges. Sleeve hole diameters, big D, and shaft, small d, with K ways are controlled element by element with smooth limit gauges. The depth of the K grooves of the hole and shaft is controlled by depth gauges, and the width of the K groove is controlled by groove gauges. The width of the groove and deviations from symmetry are controlled by complex gauges, a prism gauge and plug gauge. You can see a complex gauges. Inspection of product with K-ways using complex pass-through gauges shows the following. A K shaft is suitable if the prism gauge fits into the groove, pressing against the surface of the shaft. In this case, the shaft diameter width and depth of the K shaft should not exceed the limits. A bushing with a K-way is suitable if the plug gauge fits into the controlled hole. While the diameter of the bushing hole, width and depth of the groove do not exceed the maximum dimensions. On the figure 15.24, you can see control of K-way in the bushing using gauges. Inspection of spline connection elements. Next item. It's inspection of spline connection elements. Inspection of spline joints is carried out using complex feed-through gauges and universal measuring instruments. The outer diameter of the shaft, the inner diameter of the sleeve, the thickness of the shaft splines, and the width of the hole cavities are controlled differently using smooth boundary gauges and universal measuring instruments. The means and methods for measuring the outer diameter of a spline bushing are basically the same as for inspecting smooth shaft and holes. The thickness of the splines is measured with universal instruments, micrometer, horizontal optimeter, etc. The width of the grooves between splines is most often controlled by final gauge blocks. On the figure, 12 point, it's not 12, it's 15, 15.25. You can see measuring spline bushing and shafts using universal measuring instrument. Universal measuring instrument like indicator heads. And on the figure 12.26 or 15.26, it's control of lead and connection using gauges. You can see gauge for controlled outer diameter, gauge for controlled inner diameter, small d, and gauge for controlled the width of the spline, so the parameter B. And for the holes of bushing, you can see the gauge for controlled outer diameter, big D, gauge for control inner diameter, small d, and gauge to control B. It's the width of the spline. When using complex gauges, the hole is considered suitable if the complex plug gauge passes and the diameters and width of the groove do not exceed the established upper limits. The shaft is considered suitable if the complex ring gauges passes and the tooth diameters and thicknesses do not exceed the established lower limits. Next item, monitoring gear accuracy parameters. Gear accuracy parameters. So, gear inspection is of great importance to improve the reliability and durability of gears. For each accuracy standard, the standard defines the main gear deviations that affect this standard. In total, standard defines 24 errors that are subject to control. Gears are controlled by complex instruments and devices for element-by-element checks. During element-by-element control, individual gear parameters are checked. Meshing pitch, angular and circular pitch, tooth profile, common normal length, tooth thickness, etc. To check the engagement pitch, pedometers, flat, tangential, and edge measuring tips are used. On the figure 15.26, you can see the scheme for measuring pitch deviation in on-air pedometer. This distance, it's a pitch of the gear. Control of angular and circular steps is carried out by overhead and stationary pedometers. Overhead pedometers are usually based on the circle of protractions or depression and do not provide highly accurate measurements. Therefore, preference is given to stationary pedometers. The length of the common normal can be measured with a caliper or micrometer with special tips and normal gauges. A gear micrometer differs from a micrometer for external measurements in that it has flat disc attachments measuring ranges from 0 to 25 millimeters, from 25 to 50 millimeters, from 50 to 75 millimeters, from 75 to 100 millimeters. Control of the length of the common normal is carried out by using a micrometer with cupped jaws to cover a straight segment between two different lateral sides of several teeth. By checking the length of the common normal, they get an idea of the size of the ring gear, the thickness of the teeth, the lateral clearance in the gear, etc. The normal gauge consists of a rod 1 onto which a split sleeve 2 with a jaw 3 is mounted. A movable jaw 4 is installed in the body, the movement of which is transmitted through a transmission mechanism mounted in the body to the tip of the indicator 5. You can see indicator 5 and you can see parameter W. Skim to measurements with a standard gauge. The normal gauge is adjusted to the nominal length of the common normal along the block of plain parallel final gauges. The thickness of the tooth is measured along a constant chart using caliper gauges. Measuring tooth thickness along a constant chart is a commonly used method for checking tooth size. The essence of the method is to measure the chart size between the left and right sides of the tooth and a given height. The thickness of the tooth is measured precisely along the constant chart. Since its size and distance to the top of the tooth do not depend on the number and angle of inclination of the teeth, and the calculation formulas for spar and helical cylindrical gears are the same. A constant chart emerges if from a point on the dividing circle D, draw normals OA and OB. Let's see the figure. OA and OB for different tooth profiles. Segment AB connecting the intersection points of normals OA and OB with profiles. There is a constant chart S suffix C. And the height from the top of the tooth to the constant chart is equal to H suffix C. HC and SC. You can see the measuring tooth thickness along the chart with a caliper. The outer diameter of the well is usually set to a fairly coarse tolerance, and this makes it necessary to take HC into account when setting the size a certain correction on the caliper gauge. The measurement accuracy is limited to 0.05, 0.1 millimeters, from 0.05 to 0.1 millimeters due to the rather raw division value. A tangential gear gauge, like in figure 15.31, consists of a body to which a collet is attached for installing an indicator with an extended tip. You can see indicator with an extended tip type. The measuring jaws and instruments are driven by a common screw with right hand and left hand threads. This allows you to move both lips in opposite direction at the same time. The jaws are moved by turning the screw head. In the desired position, the jaws are fixed with stoppers. Tangential tooth gauge is a relative measuring device. Pre-installation of the tangential gear gauge is carried out according to the sample, which calibrated rollers of a certain diameter are usually used. To determine the magnitude of the radial displacement of the original contour, tangential gear gauge is equipped with an indicator, the axis of the rod of which is the bisector of the prism angle. Since the side surface of a tangential gear gauge are the profile of a toothed rail, when the gear gauge is applied after preliminary installation according to a sample to a tooth, the contact points of the wheels under test will be located on the engagement lines in exactly the same way as when the rack and wheel are backlash free. The radial runout of the ring gear is controlled using a B meter. Measuring the radial runout of the ring with beater. Position number 1, it's indicator head. Position number 2, glides. 3, bar. 4, front dragonfly with a fixed center. 5, rear dragonfly with a movable center. Fixed center and movable center. Measuring head. 6, it's measuring head. 7, measuring carriage. And 8, measuring tip. 9, 10, handless. The profile of the teeth is checked with involute meters. Figure 15.33, individual disk involute matter. Position number 1 is measuring tip. Position number 2, recording device. 3, controlled wheel. 4, rolling disk. 5, carriage. 6, tooth profile. And 7, profile error. Comprehensive monitoring of kinematic error is carried out using special devices in a single profile clutch. The operating principle of such a device is shown in figure 15.34. Device for complex monitoring of single profile. In mass and large-scale production, a comprehensive check of gears in a two-profile intercentrometer engagement is used. One body, movable carriage with a measuring wheel on a mandrel. 4 handle. 5 indicator head. 6 measuring wheel. 7 measured wheel. 'You can see measured wheel. 8 and 9 it's mandrel. 10, 15 millimeter and vernier rulers. The measuring carriage, under the action of a spring, presses both gears, creating a teeth engagement. When the gears rotate together, the error in the measuring center distance is recorded on the indicator scale. The intercentrometer provides high control efficiency and the ability to determine changes in the center distance per revolution for the gear wheel. In figure 15.36 shows modern computerized measuring instruments for comprehensive verification in one institution of all indicators of gear accuracy. Accuracy parameters are displayed on the display and on paper in the form of tables and graphs. Devices for comprehensive testing of gears. Next item of our lecture, surface roughness control. Roughness under production conditions is assessed using different methods. One of the most common is the comparison method using a roughness sample. Comparison method. The essence of this method is to compare the controlled surface with the surface of a specially made standard, a roughness sample. Roughness samples are metal plates with a flat of cylindrical working surface measuring from 30 to 20 millimeters. The working surface of each sample is processed in one of the following ways. External point, internal boring, countersinking, planing, milling, grinding, round flat and or internal. Comparison of the surface of the part and the sample is carried out visually. Reliable testing results are available only for surfaces with a roughness parameter RA up to 6.3 microns. The use of a magnifying glass provides an assessment of roughness at RA up to 0.32 microns. Instead of roughness samples, a finished part is sometimes used, the surface roughness of which is certified by special measuring instruments. Appearance of roughness samples. The method of comparing the controlled surface with the surface of the sample requires certain skills and does not guarantee determination of the roughness class with high accuracy due to differences in the sensations of the controllers. As for the use of the instrumental testing method, at present, to measure surface roughness parameters, contact and non-contact optical devices for simultaneous profile transformation, microinterferometers, light and shadow section devices, as well as raster measuring microscopes are most widely used in practice. Contact measuring instruments for sequential profile conversion are the most advanced instruments for measuring surface roughness parameters, allowing the measurement of all roughness parameters regulated by the standard. Depending on the functionally devices of this classification group are divided into profilographs, profilometers, and profilometers. A profilometer is a contact probe device designed to determine the numerical values of surface roughness parameters. You can see a profilometer on the figure 15.38. Profilometer. And profilograph. Profilograph you can see on the figure 15.39. A profilograph is a contact device designed to record the coordinates of profile points of the surface being measured in the form of recording a surface profilogram. Profilograph profilometer is a contact device designed to record the coordinates of the profile points of the surface being measured and determine the numerical values of surface roughness parameters. You can see this device on the figure 15.40. It's profilograph profilometer. The operating principle of contact measuring instruments for sequential profile conversion is based on palpation of the surface under study with a diamond needle with a very small radius of curvature or at the apex from 2 to 10 micrometers and converting using some measuring transducer, the electrical principle of mechanical vibrations of the needle into proportional changes in electrical voltage. A schematic diagram of a device with an inductive measuring transducer is shown in figure 15.41. The magnetic system of the measuring transducer of the device is formed by a double W-shaped magnetic core with two inductance coils and an armature. A diamond probing needle with a probe is fixed to the armature of the differential inductive converter. The force of the needle on the controlled surface is regulated by a spring. During the measurement process, the transducer moves parallel to the controlled surface via a drive mechanism. The diamond needle, feeling the irregularities of the test object, oscillates together with the armature. The signal taken from the indicators depends on the clearance between the oscillating core and the armature. The output signals of the bridge measuring socket enter the electronic unit of the profilometer, where they are automatically processed. The final elements of the measuring chain are reading and recording devices that serve to display measurement information. There are non-contact optical methods for measuring surface roughness. They are divided into light section and interference methods. With the light section method, the controlled surface is illuminated with a narrow strip of light plane. The contour of the surface profile is the form of section line of a light plane with a controlled surface curved by micro irregularities can be viewed with significant magnification. The optical method of light section, you can see on figure 15.42, allows you to observe a greatly enlarged profile of irregularities in the eyepiece and measuring them using a scale micrometer determine RA and RZ. For measurement using the light section method, a double microscope is used. The microinterference method is implemented using devices M2, M24, M25, M215, M29, M210, intended for laboratory measurements of RZ parameters and S and photographing micro roughnesses of clean surfaces with RZ is equal 0.03 to 1 micrometers. With the microinterference method of measuring roughness, the measured surface is examined through a microscope and at the same time interference fringes are superimposed on the image of the surface, distorted depending on the surface roughness. The height of the irregularities is determined by the curvature of the interference fringes. Microinterferometer has a massive base on which a table 1 with micrometric screw 3 is installed. Product 2 is placed on the table, fringes are changed with the surface being tested, facing down. Screw 6 focused the device by tuning the housing 4 and screw 5, the width and direction of the interference. Recently, devices have operate that can measure surface roughness using the 3D scanning method. A 3D optical profilometer, confocal microscope, is in fact an optical three-dimensional profilometer that combines confocal and interferometric technologies in one device. When measuring roughness on such a device, it is possible to obtain information with an image coded by color depending on the depth of the profile, which allows you to obtain a pseudo-color image with qualitative information about the surface profile. The advantages of the technology is also high measurement speed. You can see on the figure 15.44 3D optical profilometer. And the last item of our lecture is selecting a measuring instrument for monitoring the geometric parameters of the parts. To obtain a reliable result, it is necessary to use only measuring instruments with standardized metrological characteristics during inspection. The same metrological task can be solved using different measuring instruments, which have not only different costs, but also different accuracy and other metrological characteristics, and therefore give different measurement results. Measurements using measuring instruments of insufficient accuracy lead to the fact that part of the suitable products is rejected, or on contrary, defective products are accepted as suitable. The use of overly accurate measuring instruments is not economically profitable, since it increases the cost of product control. So, it was, excuse me, that not last slide. Determine the choice of measuring instrument. First, type of production. In individual and small-scale production, it is advisable to use universal gauges and agents. In large-scale and mass production, special mechanized and automated means, templates, and gauges. Performance and cost of the measuring instrument. These factors are taken into account when comparing all measuring instruments that can be used in a given particular case. The measurement range of the measured quantity. Measurement conditions. Operational properties of measuring instruments. The cost of measuring instruments and maximum error of the measuring instrument. The maximum error of the measuring instrument is selected based on the largest permissible measurement error B, which includes all components that depend on the measuring instruments, temperature deformation, and their basin location relative to the part being monitored. That is all random and unaccounted systematic measurement errors. The value of the maximum error of the measuring instrument, D, will be determined by the chosen measuring instrument, and the permissible error of the measurement results 8 depends on the tolerance of the measured parameters. The maximum error of the measuring instruments must be less than the permissible error of the measuring results. It is advisable to choose less than 0.1 tolerance of the controlled size, IT grade. However, the higher the accuracy of measuring instrument is needed, the more complex and expensive it is, and the more requirements there are placed on the conditions of its use. Therefore, for practical use, universal measurement instruments for practical use are selected in such a way that the permissible measurement error does not exceed 25% of the size tolerance. So it was the last slide of our lecture. The time of our lecture is finished. Have your questions about our team? Well, if you have the questions, you can write it to our Telegram group. You can write to our forum on the course. And for now, our lecture is finished. See you next time. Goodbye. Have a nice day.